lose visual reference with the horizon, and human equilibrium fails in minutes. Plunge into a solid cloud bank, and outside visibility drops to absolute zero. Survival in this environment relies entirely on a single strict equation: power plus attitude equals performance. To translate that mathematical reality to the pilot, engineers developed the standard 6-pack of analog steam gauges. These instruments divide into two specific physical families. One half measures variations in static and dynamic air pressure. The other half harnesses the physical properties of gyroscopic inertia. But these mechanical proxies are bound by the laws of physics. They drift, they lag, and under certain physical forces, they will lie directly to the pilot. Instrumental flight requires a dynamic awareness of these mechanical limitations. The pilot must continuously calculate and correct for inherent physical errors in real time. This is the attitude indicator. It is the master instrument in the cockpit because it provides the sole direct visual representation of both pitch and roll. The core is a self-erecting gyroscope spinning on a vertical axis. At operational speed, its inertia locks it in place. The gyroscope and artificial horizon line never tilt. Instead, the instrument casing and the entire aircraft pivots entirely around that rigid center point. But that rigidity has a vulnerability: gyroscopic precession. When the aircraft maneuvers rapidly, it exerts artificial gravity forces on the internal self-erecting mechanism. Shove the throttle forward to rapidly increase airspeed, and those linear acceleration forces briefly tilt the gyroscope off its vertical axis. The horizon line dips down, presenting the pilot with a false climb indication. Turns induce a similar error. Roll out after holding a 180-degree turn, and precession leaves the instrument displaying up to a 5-degree bank error in the opposite direction. Because the master instrument lies under heavy G-loading, the pilot must scan the altimeter and vertical speed indicators during any rapid acceleration or turn to verify the true attitude of the aircraft. This is the modern heading indicator. It provides the directional stability that a standard magnetic compass lacks, solving the erratic swinging caused by magnetic dip and acceleration. While the attitude indicator relies on a vertical axis, the heading indicator utilizes a gyroscope spinning on a horizontal axis to hold its position in space. This horizontal rigidity creates apparent drift. The gyroscope points relentlessly at a fixed location in space, ignoring the planet beneath it. As the Earth rotates, the gyro remains fixed, but the displayed heading inevitably drifts away from actual magnetic north. To counter apparent drift, the pilot relies on manual calibration. Every 15 minutes during steady, level flight, they read the raw magnetic compass and manually dial the heading indicator back to reality. Modern aircraft automate this process using a remote indicating compass. A magnetic flux detector mounted out in the wingtip continuously detects the Earth's magnetic field and automatically slaves the gyroscope back to north. The gyroscope guarantees short-term physical stability for blind flying, but it requires constant external calibration to deliver long-term directional truth. We move outside the airframe to examine the pressure-based instruments, starting with the pitot tube. As the aircraft flies, high-speed ram air forces its way into the pitot tube and expands a metallic diaphragm. Simultaneously, undisturbed ambient air enters the static port to fill the sealed instrument casing surrounding it. The physical difference between the ram air pushing the diaphragm outward and the static air restricting it is dynamic pressure. The airspeed indicator translates this expansion into knots on a dial, but the mechanical gearing makes an enormous aerodynamic assumption. It assumes the air density outside the aircraft remains at a constant, standard sea level value. This chart shows indicated airspeed diverging from true airspeed. As altitude increases, air density drops. To maintain pitot pressure, the aircraft must travel faster. Indicated airspeed dictates physical aerodynamics like lift, while true airspeed is your actual speed across the map. Pilots manage this discrepancy with a mental rule of thumb. To estimate true airspeed, increase the indicated airspeed by roughly 2% for every 1,000 feet of altitude. The speed reading that keeps the airplane flying safely is rarely the actual speed it is traveling through the atmosphere. These are the power indicators, showing the mechanical input variables like engine RPM and manifold pressure. They complete the original equation. The pilot sets the power, controls the attitude via the gyroscopic instruments, and validates the resulting aerodynamic performance by reading the pressure differentials. Step into a modern glass cockpit, and the physical dials have been completely replaced by digital display screens. At the top of these displays sit the flight mode annunciators. These text fields tell the pilot exactly what the autopilot computer is currently commanding the aircraft to do. But beneath the perfect digital rendering and the automated flight modes, the aircraft's computers are still flying based on the exact same analog pressure differentials and physical gyroscopes. Proficient instrument flying demands an active mental model. The pilot interprets digital readouts through the lens of raw physics, a thinning atmosphere, and the rotation of the Earth.